Hi, this is going to be a short video over the beginning chapter of Sequences and Series, chapter 11 in our Algebra 2 book. And for lesson 1, we are simply investigating sequences and series and learning to write them and read the instructions for what they are. So a sequence is simply a list of numbers. If I was to write a list of numbers, 1, 3, 5, 7, and 9. And we looked at this list divided by commas, and we saw that there was something in common with them. That for me to go from the first number to the second number, we are adding 2. The second to the third, we're adding 2. The third to the fourth, we're adding 2. And the fourth to the fifth, we're adding 2. If there is a part that is in common, we can call this a sequence. Now, if we have a list of numbers, maybe 1, 5, 7, 11, 13, 15, and 16, this is also a list of numbers. However, when we are going from one number to the next, they have nothing in common. There's no pattern and no way to get from the first number to the second number and make that consistent all the way down your line. This is not a sequence. So first and foremost, we have to have a pattern for there to be a sequence. And just because there is a list of numbers does not mean that there is a sequence there. Sequences can be defined with two different terms. We can have a finite sequence. In this case, our sequence is only 5 numbers, so that makes it finite. Or we could also have an infinite, meaning that there was typically an ellipsis, a ... at the end, meaning that it goes on forever and ever and ever, and it never has a stopping point. So if it has a stopping point, we have a finite sequence. If it does not have a stopping point, we have an infinite sequence. Now, sequences can also be determined by how the numbers are related. If the numbers from one to the next term are related with something that is an addition or subtraction, as this one is, it is called an arithmetic. Which I totally spelled that wrong on my thing. There we go. Sometimes you'll hear it say arithmetic sequence. Now, if the numbers are related through some sort of ratio, and we know that ratio is tied to the word rational, and it just simply means a fraction. That's all it means. So we can write any number as a ratio, any number as a fraction. We could have maybe 1/3. So if it is tied to each other through a fraction, which we know this has to be multiplication or division. So if we are looking at maybe a sequence, if we have 1, 3, 9, 27, and we're looking at this as times 3 as we go from one to the next. So when it is done through multiplication or division, we have geometric. Geometric. I'm not an English teacher or spelling. So geometric sequence. The reason that these two names are different, if you think about old school reading, writing, arithmetic refers to a summation or addition and subtraction. Geometry deals with shapes. And shapes have an area. Area is found by multiplying, say 2 and 2, and we'd have an area of 4. Geometry is found with our area of multiplying sides. So anytime we have something that has to deal with multiplication and division, we are going to say this would be a part of geometry, so it's geometric. If it's just addition and subtraction, it's a summation, so it is an arithmetic sequence. Okay. Now, the difference between a sequence and a series, and these are very closely tied, so we will go back and forth between these terms. A sequence and a series is when, as we have a sequence, and we take out the commas where it is just a list of numbers, and we replace that with an addition sign. Now, for a series, it doesn't matter what type of sequence it is. Remember, our sequence type, arithmetic or geometric, is completely tied to how the numbers are found from one to the next. However, when we are looking at a series is always added. It is always when those numbers are added. So the type of sequence determines how you get from one number to the next. I call that jumps. What are we jumping by? But our series is done through adding or subtracting. So as we address sequences and series, often they will go ahead and give you the expression for the sequence. They will tell you how to find the next number. And that's what it means when it says we are writing the expression for a sequence. In this case, it is usually written as a sub n equals some value that relates in. So if we did n plus 1, we're going to break down what this means. A sub n equals n plus 1 is often confusing when we have come from a background of solving lots of equations. So what if we rewrote this as f of x equals x plus 1? Does that look more familiar? In this case, we would know if we had a table of values and I had x and y values that I would plug in an x term, say the term 0, value 0 for x, and it would say that my y value when x equals 0 is 1. And I could go down the line and say if I plugged in 1, then my value would be 2. In the same way, this is how our sequences work. So our a sub n is actually your term value. So what if we kind of turned this on the side and we said that these were x's and these were y's? So we're taking our table and we're turning it on the side. And my x terms are always going to start at 1, and they're just going to move up the line. This is also in relation to a graph. So I have value 1, 2, 3, 4, 5. And if I had a line that is y equals mx plus b, that's our standard linear equation line, we would know that if we said when x is 1, what is our y value? When x is 2, what is our y value? When x is 3, what is our y value? That is what we are finding. We are saying the first term, this is giving us a location. It is a term location. However, it does correlate to a location on a graph. It does correlate to our equation because our term location is our variable value that we are plugging in to get an actual amount, which would be our y value. So in this case, a sub n equals n plus 1 is really telling us at the term location a sub n. Let's put a real number in here. If we do a sub 3, our n value, notice it has to be the same, would be 3 plus 1. This is saying at the third location, or when x equals 3. So I'm going to be looking at the third location of my sequence. The third number in my sequence is going to be what? Well, according to our expression here, it says that at a sub n, whatever my n value, in this case was 3, I'm going to plug that value in. So if I rewrote it as f of 3, we would say 3 plus 1. So I've got n plus 1, 3 plus 1. So my value at this third location would be the number 4. And we would be able to use our expression here to find any value along that sequence. Let's look at another one. Say we looked at a sub n is equal to n plus 1 squared. So again, our n values are those locations. So these are our x values. If I said f of x is equal to x plus 1 squared, and I know I have to start at 1, and I'm just moving up by our counting numbers 1, 2, 3, 4, 5, because we can't have half of a location of a term in the sequence. It's either the first term, the second term, the third term, the fourth term, or the fifth term, kind of like standing in a line. So at my first term, when n equals 1, what would I have? I would have 1 plus 1 is 2. 2 squared would be 4. When n equals 2, I'm going to plug it in. When n equals 2, 2 plus 1 is 3. 3 squared says my second term would be 9. So I could rewrite it as a sub 1 equals 4. A sub 2 equals 9. A sub 3 is going to equal 3 plus 1 is 4. 4 squared is 16. And we could move down our line and we could find any term that we wanted because we have the expression that tells us how to find that term. Right. So what do we do when we don't have the expression to find that term? Well, there are a couple of different ways to do that. One is simply by looking at the numbers that we are given to see if they have anything in common. So for example, we have 1, 10, 100, 1,000. Can we decide that these numbers have anything in common? And because we know that our expression must be written in relationship to the term value, I like to go ahead and draw my lines and put my term value underneath. So what we basically have is we have our x values and we have our y values, and we're asking ourselves, how do I get from x to y? How could I write a function? In this case, we write it a sub n. That is a rule that says when I plug in this x value, so somehow I'm going to have my n value in this expression, and it will get me the number on top. Well, in this case, we have a geometric function because as we look, it is actually by multiples of 10. So if it's a geometric function and we're dealing with multiplication and division, that means my expression is going to have some sort of multiplication or division involved in it somehow. Okay. Now, what parts of that will be there? Well, there's no constant that I'm multiplying, like no way to go from the first term to the second term. And we have to look at using our n terms. So could we say, what times 1 gives us 1? Well, that would be 1. We'd have to make it consistent. 2 times 1 does not give us 10. So multiplying times 1 is not going to work. Could we rewrite our top numbers differently? Let's rewrite our top numbers as 10 to the 1, 10 squared, and 10 cubed. Now we have a consistent base, and we have numbers that look like they are related to our n values. Could we rewrite 1 as a base 10? Yes, we could say 10 to the 0 because any number to the 0 is equal to 1. So now that we have rewritten them, we can say that our expression is some base 10 raised to some power. Can we write the power in terms of our n value? Well, here my n is 1, but my exponent is 0. My n is 2, but my exponent is 1. My n is 3, but my exponent is 2. Oh, we can notice that our exponent is always 1 less than n. So we could say this sequence can be found by taking 10 and raising it to the n minus 1 power. And now that we have a generic expression, we can find any term. If I wanted to find the 100th term, I could say it is found by doing 10 to the 99, 100 minus 1. And that would give me the 100th term in this sequence. Okay. Now, as we take our sequences and we move them into a series, we have more new information. So just as we related our a to the n and our expression to our old f of x function, we've got to learn how to read our new summation formation. So summation is written as sigma. This is the term sigma. It tells us to sum it up or to add. So what we know is that it is giving us instructions to add up a bunch of numbers. So what numbers do we add? On the bottom, we have limits. So we have a lower limit and we have an upper limit. Okay. Our lower limit tells us where we start in our sequence. Now, it's very convenient to start at number 1. So if in this sequence, I have a sequence of 6 numbers, if I wanted to add them all up, I would start at 1, I would end at the 6th value, and I would add all of them up. Our limit also will typically have an I equals. It could have n equals that term. It is telling us which value we are going to start at. Often you might see different variables down here. Okay. And so the reason they use I is it is called the index of summation. So they take that I. I know we've seen I previously as imaginary numbers. That is not what this is saying whenever we have a series added up. It is simply the instruction guide of what numbers to add up. If I only wanted to add the second, third, and fourth term, then I would change and I would say I'm going to start at the second term. I just want to add these 3 numbers, second term, and I'm going to end at the fourth term. If instead I wanted to add the third through the 6th term, I would start at the 3rd term and I would end at the 6th term. So in our sigma notation, in our summation, it is giving us an instruction guide. Now, if we are starting at 1 and we are adding everything in that series, so it's all of them included, you will also often see written just an S with an N at the bottom. And this also means to sum up however many terms. Our N will be given as our last term, and it's an unwritten one. It's saying from 1 to N. So in this case, we would say sum up the sum of 6, the sum of 6 terms of this sequence, and it's going to have that same expression. So it is important for us to know the expression of how to get the numbers for our sequence to be able to use it in our series. So that is why they are so very closely tied together. So on some of our homework, it says to write the summation notation. So what they have given is they have given you some numbers, maybe 1, 5, 9, 13, and 17. We notice that it is a summation because they have put plus signs between them, indicating that we need to add it up. So we're going to immediately write our summation notation. They want all of these numbers. So how many do we have? We start at value 1. So this is 1, 2, 3, 4, 5. We have 5 terms, so it's going to go from 1 to 5, all 5 terms. And then we need to write the expression. And the expression tells us how to get these terms. So we're going back to that sequence notation and saying, how do I go from the first one to the second one? And how do I do it in relationship to the second one? Well, we talked a bit before about being able to just look at it and figure it out. So kind of a Sherlock Holmes introduction for that. I'm not going to cover the actual formula for finding that because we're going to do that next in 11.2. So in this one, could we look at something that would be common? If I multiplied 2 times 2, that would give me 4, and I could add 1 and get 5. So would that always work? Could I multiply times 2 and add 1 to get 5? 3 times 2 is 6, plus 1 gives me 7. So that doesn't quite work. Could I multiply times 3 and go backwards? 2 times 3 is 6, minus 1 gives me 5. 3 times 3 is 9, minus 1 gives me 8. So that doesn't quite work either. So we're going to keep working our way up. I also know that I am jumping by 4. And typically our jumps, what we are jumping by, gives us a clue on what needs to be in our expression. So what if I multiplied times 4? 2 times 4 gives me 8. How do I go from 8 to 5? I would need to subtract 3. Okay, so if I did 4 times n minus 3, does that work here? I've got 4 times 1 gives me 4, minus 3 gives me back to 1. 3 times 4 gives me 12, minus 3 back to 9. 16 minus 3 back to 13, 20 minus 3 back to 17. Okay, that's working for all of it. So our expression to find each number is 4n minus 3. And we simply we write that expression just right here in the front of our sigma notation. And this is our entire summation notation for this addition of these numbers. Okay. If they have already given you a summation and they tell you to actually add them up, for your homework problems, you do have some that get a little bit longer. So for example, number 44 says to sum up the first through 6 terms of 3i. So we've got 6 terms, 1, 2, 3, 4, 5, 6. The first term, we're simply plugging our numbers. 1 times 3 is 3. These would be our values. 2 times 3 is 6. 3 times 3 is 9, 12, 15, 18, and we're going to add all of these up. You may use your calculator for your homework and just go ahead and add them up if you would like. One of the things that we have addressed, and we'll address a smidge more in 11.2, is that when we are summing a sequence, when we pair up our terms from the beginning to the end, they will always equal the same amount. So 18 plus 3 is 21. 15 plus 6 is also 21. 9 plus 12 is also 21. So instead of adding up 6 numbers, I only have to add up 3. I have to do 21 times 3, and that would give me my sum of all of those numbers. Okay. What if they give us the summation of 1 to 4, where k equals 1. See, we've changed our value, but then our expression, as long as it's written in that value, works. K times k plus 2. What does that look like? It means we have 4 terms, correct? If we had them written out, we are adding these terms together. What is our first term? We're going to plug 1 in. So 1 plus 2 is 3. 3 times 1 is 3. If we plug in 2, 2 plus 2 is 4. 4 times 2 is 8. I'm going to plug in 3. 3 plus 2 is 5. 5 times 3 is 15. And then 4 plus 2 is 6. 6 times 4 is 24. So these are our new numbers. Now, when we have bigger jumps, when we have something that is multiplied and added, does our pairing still work? Well, let's see. 3 plus 24 is 27, and 8 plus 15 is 20. Oh, sorry, guys. I'm tired. 23. There. Okay. So our pairing in this case didn't work because we had a multiplication in there. So when we have some multiplication involved in our series, we're going to have to double check and make sure that what we're working with will actually pair up if we can fully use our arithmetic notes and stuff. So in this case, we're just going to simply use our calculator and we're going to add up those terms. Okay. There is one in your homework that is written, the summation of n equals 1 to infinity. That means this is going to go on and on and on forever. N over n squared minus 1 over n. And they're saying, what does it add up to be? So let's look and start writing out a couple and just see what it looks like. When n equals 1, we have 1 divided by 1 minus 1 over 1. And we can see that that is simply 0. So let's look at this way. If n equals 2, we have 2 divided by 4 minus 1 over 2. Okay, we need to change this to the same denominator. So that's going to be 2 over 4. Oh, we've got 0 again. Let's try 3. I think I see a pattern. 3 over 9 minus 1 over 3, which is 3 over 9. We've got 0 again. So no matter what number we plug in, we're going to get 0. And when we add them all up, we're simply going to have 0. Okay, so for when we have to actually write this out from a word problem, how do we decipher what they are saying in a word problem to write out in a sequence or a series? Okay, so on your homework, it gives you a nice little triangle, maybe a truss for a house, and it's dividing it up, and we're going to have equal amounts. Go back and forth. And it tells you to find the total length of the vertical supports from one end to the middle. And on the bottom, it gives you the length. So this one is 1, 2, 3, 4, and 5. So then we would go back down. We obviously have a pattern here. We are adding by 1 for each of it. And it says, find the total length from one end to the middle. So if I were to write this in summation form, I would say I'm going to sum from 1 to 5. And what is my expression? Well, for the first one, it's 1. For the second one, it's 2. For the third, it's 3. So it's just equal to itself. So n equal 1 is just simply equal to n. The actual term place is the same as the value at that term location. So how would we sum this up? we would say we're going to do 1 plus 2 plus 3 plus 4 plus 5. Because there's no other multiplication, we can use our pairing method. See, 1 plus 5 is 6. 2 plus 4 is 6. And then we have a 3. So we've got 12 plus 3 gives us 15. Okay. And then it says, find the total length for the vertical supports from end to end. So now we're going all the way across. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. If we were to rewrite this in summation notation, I would now have 9 terms. However, I can't use this expression because I have one expression going up and then I have a different value going down. So we cannot use our series notation to address this list of numbers, because when we actually write out the list of numbers, the first 5 terms are a sequence. The last 5 terms are also a sequence. However, the entire 9 terms are not a sequence. So we could use our summation to find the first 5 terms. We could then again use summation to find the last 4 terms and add them together. Or in this case, because it's small numbers, we can just add them all up on our calculator. Okay. So hopefully that gives us a great intro to sequences. You can go ahead and stop here. I am going to work 67. It's a bonus question on your homework if you'd like to stick around for that one. Okay, it says, in the puzzle called the Tower of Hanoi, the object is to use a series of moves to take rings from one peg and stack them on another peg. I think often maybe at the Science Museum you've seen this. They might have different pegs and they have rings. And you've got a couple of different rings, and it's asking you to stack them maybe all on the center ring in a certain order. Babies have this, they've got the bigger rings, and they're going down like that. So there's actually a pattern to this that tells you the minimum number of moves that you have to make. It says that the minimum number of moves to move in number of rings. So if we had 1 ring, so this is how many rings, these would be our X values, right? And this is the number of moves that it takes to move those rings. For 1 ring, I have to move at least 1 time. If I have 2 rings, I have to move at least 3 times. If I have 3 rings, I have to move at least 7 times. And if I have 4 rings, I have to move 15 times. For 5 rings is 31. So they have given us the numbers in our sequence here. And it says, find a formula for this sequence. And then it asks a question, what is your answer here for 6? What is the minimum number of moves for rings, for 6 rings? Okay. So what are we doing? Let's look. We are adding 2 here, and then we're adding 4, and then we're adding 8. So we do not have a sequence that is an arithmetic sequence. We've got something that's geometric. It's dealing with some multiplication. Something that we see with multiplication is that the jumps actually have a pattern. This is 2, this is 2 squared, 2 cubed, and we would see here that we've got 16, which is 2 to the 4th. So I'm just going to put down 2 of something, 2 to the n, because my jumps definitely have 2 to the n in common, and see if I can come up with these values here. So 1, what could be our n? I always just start with the original one. So 2 to the 1 gives me 2. How do I get to 1? I would need to subtract 1. Let's see here. I've got 2 squared gives me 4 minus 1 is 3. 2 cubed gives me that 8 minus 1 is 7. 2 to the 4th gives me 16 minus 1 is 15. It looks like 2 to the n minus 1 is our value for our expression. So in using that, what is a sub 6? Remember, 6 here is our n value. We would plug it in and say 2 to the 6 minus 1 is going to give us our value at a sub 6. And you would plug that in as your answer.